Okay, thanks for coming. This is Nicky. He's a researcher at NIST, and he'll be talking about some of his work in finding this vulnerability in SHA. And just as a reminder, this is a public tech talk.
Thank you, James. Take it away. So I'm going to talk about hash functions. Most hash functions that are being used, like say maybe like virtually all hash functions used in practice are iterated hash functions. So what happens is you take a message, and then possibly after padding, you split that message up into blocks of a particular fixed size. You process all of those one by one, so that you eventually end up with a hash value. Then I added this little fingerprint symbol here to indicate that it's supposed to be that the hash value uniquely identifies the file. So it's not supposed to be that you can work yourself backwards from a given hash value, or that you can find two inputs that map to the same hash. So typically hash functions are used in digital signature schemes where you sign the hash instead of the message itself. That's like a typical use case. If you want to implement a hash function, there are two interfaces that are common. One is a one-shot interface. That's the hash I'm showing at the top of the slide. And another is an incremental one. So there you have it's called first init to initialize your structure, then one or more times or zero or more times update. And when you call final, then you get what the hash would be, as if you got a concatenation of all of these inputs to update. So to make it a little bit interactive, I have a question here. So does anybody have an idea of where or when you'd use one or the other interface?
Streaming.
Second.
Yes, what do you mean by streaming, or how do you see?
Just data that you don't currently have in hand, but it's.
But you could actually use the hash interface as well, right? If you're working on streaming data.
But then you'd have to keep it all in memory.
Exactly, right? So this is basically, like I've never got it, I don't want to see this question get wrong, but I find that like the answer is a bit surprising. So the reason why you want to use this init update final interface is to avoid intermediate copies. So if you always need to use hash, then you need to store your data somewhere and you don't know how much you need to store. If you have this init update file, you can process on the go. You don't need these intermediate copies. So an important thing here to mention, but it's a bit obvious, right? It's like the size of the update does not need to be the size of the blocks here. It's just typically whatever size you have that comes in that you don't want to store separately is what you give to update. Then in cases where you have, let's say you need to hash A, AB, ABC, ABCD, it can be really efficient if you can already process what you have so far. Otherwise, you need the intermediate copies and also to run hash again. In the case of a streaming input. This is not always implemented correctly. So a first bug, I'm looking here at submissions to the SHA-3 competition. Blake was one of the 5 finalists. The bug was already present since 2008. And it's one that affected all implementations in all rounds of the competition. And only years after the competition ended, the bug was found. So if you have Blake with a 256-bit hash output size, then this first slide, this block that you have to process messages is going to be 64 bytes. Something special happens if you call first init, then update on less than a block, then update on exactly a block. And then, yeah, you need final to get the full hash. Actually, this first update will be forgotten due to the bug. So then that's quite bad, because it means that whether it was present or not present, the hash will be the same. So you're breaking one of the cryptographic properties that I was showing on the first slide. You can see this as a second preimage in terminology of cryptographic constructions, but then a preimage for the implementation, not for the specification of the algorithm, because you can modify the message and still get the same hash. So given a hash and an output, you can find another output, another input that gives the same output. Then another bug that I'd like to mention here, and this is the first CVE that I found, so I got more street credibility since working on this, is in Apple Core Crypto. where if you're looking at a hash on anything that is 4 gigabytes at least, so like what has a series of calls within one call at least 4 gigabytes, and what happens is you enter into an infinite loop. So this affected all of the devices that Apple was using, because this is part of the cryptography in their security chip, and all of the hash functions except for one, because they all share the code of doing hashing. In response, NIST introduced the LDT, large data test, to see what happens when you process a lot of data. And this seems to be something that just keeps on giving. So like after NIST introduced this test, then the labs automatically turn on this test and are checking if the implementations pass. A bug was found in libgcrypt. It's like an implementation that people at Gallo are definitely familiar with, because Gallo also did some work on this particular implementation. Here, there is failure as well if you provide a large input. And actually not so long ago in NSS, so that's Netscape Security Services, the cryptography behind Firefox, bug was found as well, processing large inputs. The one I'm going to talk about here mostly, and the one that seems to excite people more, because here you have worse things going wrong than just an infinite loop. In the case of the winning algorithm of the competition, so SHA-3 was, like Blake was one of the finalists, SHA-3 was the winning one. There is a bug where if you do a sequence of 2 calls to update, so any single call to update, doesn't matter how long it is, it's going to be fine, but like a specific sequence, where the first one is going to be X bytes, and the second one 4 gigabytes minus X. If you do this particular sequence, then what happens is you have buffer overflow happening in the implementation. And I wrote a proof of concept to show you can do arbitrary code execution with this buffer overflow. If you remove this X bytes here, then it is also leading you into an infinite loop. So it's actually 2 types of vulnerabilities depending on the input, either a buffer overflow or a loop that doesn't terminate. So I want to show the lines of code that were wrong and how they were fixed, but not actually so that you can say like, oh, the problem is obvious to me, because I think it's not, right? When I show this and I ask people, where do you think the bug is? People typically tell me, well, I guess the first line, because I see this cast to unsigned int, and that looks suspicious, right? But that's actually not where it goes wrong. What happens is that this partial block plus instance byte IO index, if you add those 2 values, it might be that some of those overflows, they're both unsigned, so that's defined behavior in C, so C will wrap around. And then when you're expecting to have a really large value, you actually get a really small value. And this check of seeing, am I larger than rate in bytes, is going to say no, where actually it should have said yes if it was an arbitrary precision calculation. So what they actually intended to do here is limit some value. In this case, if partial block is larger than a certain value, partial block is equal to a certain value. That's the first step of how the code was rewritten. But then actually, like, why would you want to compute partial block twice? Oh no, there's a lot of stuff going on. Like, to avoid that you have the infinite loop, you actually need to have not partial block, but data byte line minus I here. Otherwise, you're losing some bits. And as I was saying, to avoid computing partial block twice, you might decide to do it only once, and then either say partial block is limited to a specific value, or partial block is going to be this data byte len minus I. So that's actually going back to what I showed all the way on the first slide of how you process the input into blocks. You want to compute if there's still a little bit left that you need to store, so that if a future call completes it, that you can process the amount of data. But something went wrong here, and only if you do a specific sequence of 2 calls, because the implementation gets confused. It's thinking you get a large value and actually get a, thinking you're supposed to be getting a large value, but you actually get a really small one due to an overflow. To explain a bit how to exploit this, I have to say a little bit more about how SHA-3 is constructed. So here, this function f is the function that does the mixing that I showed on the first slide. It is cryptographic permutation, so you can compute it forwards and backwards easily. If you know the full output, you're not supposed to, because it's supposed to be a bit of the output is always going to be hidden at the end. And the message is XORed in. So you see XOR, the way that this message in blocks is being provided. So if you want to do a second pre-image, similar to what this Blake example did, then if you provide this call to X bytes and 4 gigabytes minus X bytes in the beginning, and all of those bytes are 0, then you XOR in zeros, and this call, like this beginning, the first 4 gigabytes will be forgotten as if it isn't there. So then you get a second pre-image of the implementation, basically 2 different messages, one with and one without this zeros in the beginning, that result in the same hash. Because it's a cryptographic permutation, you can also use this to construct a pre-image of any value. You just say like which hash value H here is the one that you want to have. You can then work the permutation backwards and find out what those values of M0 and M1 need to be, so that the XOR leads up to 0. So the value that you could add to get a hash of, let's say, all zeros or any specific value that you're looking for the implementation. So both of these are the vulnerability world data-only attacks. So you're not changing the flow of the execution. Here I am changing the flow of the execution by providing as part of the message also some payloads to be executed. And then I decided just to make it really, really simple to do like the most basic buffer overflow exploit, which is to do a return to stack. So then I'm adding some payload as part of the message with an address that it needs to point back that is inside the message once the stack pointer is overwritten. And this payload is executed. So like in a typical case where you want to, let's say, verify a digital signature, it doesn't matter that the signature is incorrect. As you're hashing before you check if the signature is correct, already while the hashing is going on, you take over the flow of the execution and you execute the shell code. That's how the buffer overflow exploit is constructed. But here at Galway, I think people are interested a lot into how the bug was found and symbolic execution tools and formal methods. So I do want to say a little bit about this. I used a black box tool for this. The tool is called KLEE. I'm using it in a very, very simple way. I'm simplifying a bit, but like not too much actually. All what I'm doing is I'm saying, take some symbolic state, do update once with data bit line as the size of the input, and on another symbolic state, do first an update on data bit line 1 and data bit line 2. And it's supposed to be that data bit line 1 plus data bit line 2 is equal to data length. So like it's actually processing the same message into parts. I'm adding conditions to say, well, in the beginning, my state needs to be equal. I don't know what it is. I just say it needs to be equal. And at the end, I want to see my state being different. And actually, I'm not looking at what the value of the message is. That's why you see this null in the middle. So the message is not important to me. It's code that I commented out. All I want to know is in the internal data structure what happens. And I want to see that there is a case where the specific variable that keeps track of how many bits do you still have left of an incomplete block, because that's the only one that you have that you keep track of. Is there a case where this variable is going to be different? And if so, that's the case I want to track. So as I mentioned, all variables are symbolic. I don't use the message. Something interesting here is that update can actually do a very large number of iterations. So looking at like data bit line is a 64-bit unsigned integer. So 2 to the 64 divided by block size number of iterations is the possible number of iterations that this update call can do. But apparently KLEE can figure out quite easily how to simplify things related to this loop to figure out how to see if this last statement is asserted for a specific input, yes or no. And then one thing that was an obstacle when using KLEE, and actually this is what took me most of the amount of time, is that if there's an infinite loop in the implementation, there's also an infinite loop in KLEE. So I was wondering, like, why does KLEE not terminate? Right? So like you need to instrument the code a little bit to say like, I want to make sure that if I'm seeing the same loop counter again, then that's also a bad thing. So tell me about that. And then KLEE can terminate quickly. By quickly, what do I mean? So if there's a bug in the implementation, here, like for comparison, I showed the same applied to other finalists of the SHA competition as well, and also this earlier Apple Core Crypto that I mentioned. So if there's a bug, then it takes about a second for KLEE to say, hey, here's the input that causes you to have something wrong going on. In this case, like the value that triggers the infinite loop. If you fix the bug, then it takes, depending on whether you look at the version submitted to the competition or the package that came out after the competition that got integrated into PHP and Python and other places. In the core language, like not a module of the interpreter, then it takes around like 20 to 40 seconds to show correctness, basically meaning KLEE terminates. KLEE has shown that there is no value, where you start from the same state and at the end you get two different symbolic states. There is a little asterisk, and this little asterisk is that, well, if you actually want KLEE to terminate, then the block size, if it's a power of 2, so if I set it to be like, okay, assume I'm looking at some variant of SHA-3 that processes blocks of powers of 2, like let's say 128 bytes blocks, then KLEE terminates, but otherwise KLEE doesn't terminate. And this is actually related to a way that KLEE is using particular SAT or SMT solvers in a particular way that the corresponding SMT instance is one that is not easy to be solved by the solvers. There's quite some work that I did recently in follow-up to try to overcome this issue, and also something that I was discussing with KLEE developers when I presented this at the KLEE workshop last month. Then I want to mention a little bit about CodeQL as well. So I worked together with GitHub Security Lab to see if you use the same vulnerable pattern, maybe the one that you're using in the code for SHA-3, or maybe some other code that just happens to have the same pattern. Is it actually something that you are able to detect and to fix? So CodeQL is something that GitHub offers for free for all public repositories. So you can turn on code scanning, and then there's now a query that CodeQL supports that's integrated into CodeQL that will detect this particular pattern. And as we were working on this, trying to look at false positive, false negatives, it turns out that there is another place, well, was actually, because like we fix this now, in boring SSL. This code here is boring SSL, a fork of OpenSSL. But OpenSSL has some similar code here as well, where you have the same pattern, where it's like A plus B larger than C, but you actually want to do like A larger than C minus B. So like if you rewrite the code in this way, it becomes more clear what actually the pattern is. This is not a vulnerability because you can use tools, actually the same KLEE if you want, or any other tool that you like, to show that for this particular implementation, it's part of HKDF, hash-based key derivation function. You do not actually have a case where this done plus to do can overflow, but CodeQL is not powerful enough to realize this. You need to go to symbolic execution tools. Nevertheless, like the people behind boring SSL and OpenSSL have said, well, it's good for us if we can write the code in a cleaner way. This is an obvious pattern we want to avoid. So maybe even in cases where you find vulnerable patterns, it's something, potentially vulnerable patterns is something you want to eliminate. So then to conclude, and also one of the reasons why I decided to come here and engage with Galwa is that I hope that I can give you some more insights into what the idea is of the upcoming NIST Formal Methods Within Certifications Program, FMCP workshop that we're organizing July 23 to 25 at NIST. So here the idea is basically to bring the formal methods community, X high assurance cryptography software, together with FIPS community, because whenever you have cryptography that appears in a device you want to sell to the government, if it's a laptop or a phone or a router, it needs to be something that is certified by NIST, otherwise it's not something you can sell to the US government. The idea is to bring these two communities together. You'll see a lot of the same companies, but apparently different parts of the same company who are not necessarily interacting with each other. So here are some of the topics that are definitely going to be interesting during the workshop. When I had a call earlier this week with one of your competitors, actually, most of our discussion was around the first topic, like trying to understand exactly how does this FIPS 140-3 program work? So how does NIST certify cryptography software? What is certified? What are possibilities to strengthen the techniques? There was a bit of discussion as well, and it's something that we listed in the set of possible topics for the workshop between, like, do you want to use proof assistance, or do you want to use automated solvers style SNT set? I'm happy to answer some questions as well about this regarding some recent experiments that I did. If people are interested about this. When we're looking at the upcoming post-quantum crypto standards, this is something very new. Just like 1 or 2 weeks ago, NIST announced that there are going to be some additional requirements in the implementation that are specifically intended to make the application of formal methods easier. So I'm happy to discuss that as well. And what I promised more or less in my abstract here, and what I'm also willing to discuss, of course, and what we mentioned in the workshop items, is like, well, what would be pragmatic paths to adoption using less rigorous methods? Like, what's the way in which you can see trade-offs between cost and effectiveness of using certain approaches? I guess the main thing I want to say here is that cryptography, not just cryptography, but software in general, is developed as part of an iterative process. You want to keep improving upon existing code, and then it's important to try to see how can you gradually make code more and more amenable to using formal methods. It's also possible, but a bigger obstacle, to say, well, all the code you wrote is actually wrong, replace it with this code that comes out of my code generator, and that's the right approach to go. But of course, that's an approach we need to consider as well in some places to see how to move the field forward. So this is my, well, not my last slide, because I have a lot of backup slides, but this is where I'd like to end the presentation to allow a lot of time for questions. So thank you very much for your attention.
Thanks, Nicky. I guess, does anyone have questions? I guess one question I had is, so you said if the bit lengths are not even, then it's not that there's a infinite loop in the algorithm, it's that the SMT solver is just not returning, is that right?
Okay. So what I'm looking here, because the asterisk applies to the correct code, so after the bug has been fixed.
Yeah.
So here there's no issue with infinite loops. The issue is related to the queries that the solvers get. Well, KLEE supports 2 SMT solvers. One is Z3 and the other is STP. So for STP, it's well, just names of solvers, right? I mean, Z3 is part of it's a project by Microsoft and used extensively in Project Everest, Sage, and like in a lot of the Microsoft tools. And STP is not a source, like already a really old tool. I mean, relatively old, right? In this field. STP looks only at bit factors. Z3 can support more complicated logics as well. So in the case of Z3, in the case of STP, I do not know, but that would actually be interesting how to get get STP to solve the queries that come out of this particular example. In the case of Z3, I do know how to solve it, but basically there is a pre-processing step needed to write your equations a little bit differently, and then it's possible for the solver to handle this. So like this is some ongoing stuff that I've been looking into. Once you have a power of 2, it becomes easy for the solver to see why you would have this calculation being correct, because it's just saying, look at the lowest bits and those have to be equal. But if it's not a power of 2, then you have this division that if you want to reason about it in the context of a set solver, it's not so easy to do, apparently. But maybe Eric is going to still be wrong, or like I see a raised hand.
I was just going to ask, you're calling out my hand?
Yeah,
sorry.
I see your hand is up. Yeah.
Okay, I was going to ask if any of the code that you use to verify these algorithms, like if the harnesses, the KLEE harnesses, are on any kind of public repository, or if that's all internal.
No. So the code is public. So I'm using yeah, I mean, like it works on any version of KLEE. Don't necessarily need to have the latest one. And the code is like I included in the appendix of the paper. It's like only a few lines of code to do this. But if you want, I can follow up by email and just avoid you the awkward copy pasting from the PDF, and just send you the code if you're interested.
Yeah, I think a bunch of us would be.
Yeah, sure. Yeah.
Me too.
Yeah, so I'll send the code to Spot and like can share it to anybody interested here in the meeting. It's basically the same code that I've attached to the paper as well. This is a paper I presented at ACISP last year, showing how KLEE was used to find the bug.
Have there been like vendors that have tried to get implementations certified, and the labs, as a result of the large data check or whatever, have like rejected or
yeah, exactly,
failed to certify as a result of
yeah, so like that's one of the ways in which I try to leverage what NIST is doing already. When this large data test was introduced, and I mean still today, it's an optional test. In the beginning, the labs have said, well, that's optional, so we don't actually need to do it. But after a while, like, wow, why don't we offer extra value to our customers by enabling this optional test now by default? And many implementations that previously have passed the program many times over well over a decade suddenly start failing because there's a new test vector in town now that is causing implementations to fail. So I think that's really interesting. Here I show the large data test. In the case of SHA-3, we added an init update final test to specifically test for this SHA-3 case. The code itself is completely unrelated code, but just yeah, if you haven't tested what would happen if you provide a large input, you might be surprised in the ways in which it might go wrong. Following up on that as well, like for the case of Python, the code used initially was the code that I showed here, which was the one with the buffer overflow. The people at Project Everest reached out to me to say, well, would they be interested in verified cryptography instead? And I said, like, well, I think I might know how to make that argument. So this is how now some verified cryptography got into Python. But as they were integrating this code, they failed this large data test as well. I think that's one of the main difficulties if you want to start to use formally verified implementations. So typically you have problems at the boundary between verified and unverified code. And what they had was a precondition that inputs would not be too large, and like this precondition was not satisfied as they were integrating the code. So it reminds me of this quote by Donald Knuth, like, I've only proven it correct, I've not tried it, right? So I see how there's actually complementary interest between what FIPS is doing and what formal methods approaches are doing. FIPS is actually mostly running the code on a huge amount of devices and making sure it runs fine. But I think there are possibilities to strengthen both. One of the things I've been very active in recently is adding more and more test vectors to the NIST program, and we see as they get turned on that implementation starts failing them. So it's that's, I think, an interesting interaction. So they're fixed now, and I'd mentioned the bug ID, so you can look up to see exactly which item, like which issue in the tracker is showing the change in the code. Because this is open source code, for everything closed source, we don't know if the lab tells the vendor that they failed the test vector, like we don't see the change set anywhere public. So there should be more than what we see here, but in private code.
Could you expand on the formal verification requirements that have been announced for?
So this is now announced on the NIST mailing list for post-quantum cryptography. So what I'm saying is public now, and you can look it up. It's not a lot. I mean, like, because like whenever I speak to people who have a formal methods background, you're expecting really heavy stuff, right? Like needs to have some proof of system or somewhere SAT solver running, or like in this case, it's just trying to enforce a little bit more of a type system. So the two requirements that are now in there, very basic, just related to type systems. One of them is disallowing the use of floating point operations, which you say, like, why would you use floating point operations to begin with? But actually, there is a bug in Bouncy Castle, the most widely used library for cryptography in Java and C#, where they implemented block cipher mode of operation, but for a very specific input. Due to a rounding error, floating point rounding error, you get a wrong output, and this input is difficult to find. The same pattern, the same thing that went wrong there could also go wrong in the case of post-quantum crypto. So previously, the standard had some explanation of like, because I gave this feedback, like try to avoid it. A strong recommendation not to use any floating point computations. Now that became shall not, so it's disallowed to use floating point computations. The labs are saying that in the first step, well, they probably just want to look at the code manually or using some custom tools to see if you have or don't have any floating point operations. But it's, I guess, the first step to try to get to enforcing certain requirements on the code in the context of formal methods and enforcing a certain type system. So that's one. The other is that the upcoming standards for post-quantum cryptography had an unbounded loop in there. So not an infinite loop, but an unbounded loop, statistically unbounded.
It's like the rejection
sampling. This is the rejection sampling. So quite a few people wanted to limit the number of loop iterations, but then didn't really know like what's the reason behind that or how to make the argument. It is annoying for many reasons if you have a loop for which you don't have a bound on the number of iterations. And in the context of NIST, this is the argument that I successfully made to my colleagues. Well, people are going to limit the number of iterations to the loop anyway, because we see that it's happening in implementations, and they might put this limit too low. So what NIST has already announced that it's going to do in the upcoming standards is give two options. One option is, well, use your unbounded loop if you want to, that's fine. But if you want to use a bounded loop, you need to use at least a certain number of iterations so that the probability that something goes wrong when your loop is taking too many iterations, that this probability is less than, well, the mailing list said 2 to the power minus 128. It seems that the final standard may even go to 2 to the power minus 256 to make it really, really unlikely to go wrong unless something else is wrong, like a broken chip or something wrong in the code. So this would be a type of error for which you cannot safely recover. That was most of the discussion on the NIST mailing list in response, like, oh, that's really bad if you throw an error and then what happens, right? So this is supposed to be an error for which you cannot recover because it's indicating that either the code has a bug or the device is broken, similar to not getting good enough entropy out of your system. So if you want to, as I guess many people with a formal methods background would be happy to do, say that there is limits of the number of iterations on every loop bound, then in the upcoming standard, you can do that. You can implement it in this way. So you don't need to deal with potentially infinite, potentially unbounded loop in your implementation. So these are the two ways in which we're trying to make it easier for people who want to use some formal methods approaches. It's not a lot, right? But it is in the standard. So like, it's a starting point.
I don't know what other people's experiences, but I think it would maybe be helpful for me if you gave like a 2-minute, 10,000-foot view on what the certification process looks like. Like let's say that I'm at some company and I have some implementation that I want to put somewhere and I need to get it certified, FIPS certified. What does that high-level workflow look like?
So first question is like, what is certified, right? People typically ask like, well, do you certify my protocol, my TLS, or my... It's like NIST does not certify protocols, except for some very lightweight protocols, which NIST doesn't call protocols, but calls schemes. So things like key agreement and key exchange are things that NIST checks for, but you have a very limited amount of interactions in those protocols. Something like TLS or SSH is something that is out of scope for NIST. So NIST is looking at what are the algorithms that are being used, the symmetric key and the public key algorithms that you find in your code, and very simple protocols on top of that, key agreement or key establishment schemes. Part of the requirements are to say, well, if you want to use a block cipher, let's say, you have to use AES. So like this limits the scope of the list of algorithms you can use to the one that NIST has standardized. Until last year, it used to be that triple DES was allowed as well, but as part of the decision to get rid of triple DES, so now we have only AES left. And yeah, that greatly cuts down on the possibilities in which things can go wrong with some custom cryptography. But then it's not just saying, well, you need to use AES, but also which mode of operation are you using? How do you implement this mode of operation? How do you do some requirements like zeroizing at the end when you need to delete the key? How is that being done? The reason why I'm mentioning in this way, in this order, is like there are quite a few of those things that you can do easily on a source code level using standard formal methods approaches, where you just want to not just say I'm satisfying specific test vectors, but I actually want to match the specification. Good news, by the way, all cryptography actually has a specification. So like that's a problem that we can overcome. We do actually know how the algorithms are supposed to look like. We have a standard for each of those. But it is not possible to exhaustively look at all the inputs because you will have secret keys that come in there. And secret keys need to be at least, requirement now is 112 bits long. So 2 to the 112 is not something you can generate in terms of test vectors. So you're always going to lack in terms of test coverage. And this is just mentioning the keys. Like there might be things going wrong for really long messages or for other ways in which you can imagine your algorithms to fail. Formal methods approaches are really helpful for that. And I guess I showed that in my slides here that as I was trying to prove that the SHA-3 implementation was correct, I found out the proof didn't work, and actually that wasn't correct. So like, can help to discover some bugs. So that's one approach to basically strengthen this black box testing and make it more white box. But there are always going to be, and this is actually the majority of validation that is being done on the level of FIPS 140-3, a lot of requirements that you cannot really specify on in terms of input-output behavior. And that's why I mentioned like zeroization, like did you correctly zeroize keys, or to define that keys only stay within a specific place. So FIPS 140-3 requires you to say what is the module boundary, which can be like a physical boundary, like the edge of your chip, but also more of like a logical boundary. And whenever keys are being moved in or outside of this boundary, it's like the walls of the castle, you're supposed to satisfy some requirements of how you do that. So all of that is part of FIPS 140-3. And yeah, I think it gives a lot of opportunity to strengthen things if we can avoid CVEs being found, as they regularly are in these FIPS validated modules. So if we can ensure that there are certain types of mistakes that you didn't make in your implementation.
Yeah, I think the thing that I was trying to get at was where are the biggest obstacles to integrating not necessarily the super duper heavy duty formal methods, but any sort of formal methods into the process? Is it the lab's willingness to evaluate them and include them in the package that they send to NIST? Is it NIST's is the expertise that NIST has in order to evaluate the efficacy of the formal methods tools that are being used? Like I'm wondering, kind of like, you know, if I just plopped a lean implementation of the SGCM and said, here, please certify this for me, and then I also said I'm going to run it on this system, you know, here the binary is sticking it in this part of memory, you know, like, are the labs going to say, no, I don't know what to do with lean? Or maybe they're okay with it and they send it off to NIST, and NIST goes, why should I believe that the properties that are sitting here are like actually being checked? Like, I have no idea how lean works. Or do you see what I'm saying? Like,
yeah, absolutely. Yeah. So if you look at the standard will always have statements of how things need to be implemented. Every place where there is shall or shall not, that indicates that the team that is working on those FIPS validations has to check, to the extent that they can, whether it is being satisfied. NIST does not actually do all of those checks themselves. NIST looks at the documentation that came out of the evaluation and goes through the documentation. So this does actually allow NIST to easily scale to put more requirements in there, because if there are additional requirements, it's actually the validation labs that will have to satisfy those requirements or check they're being satisfied, put that into the documentation. This doesn't have extra work except for reading a bit of extra text that they have been satisfied, which might actually make the deliverable at the end quite a bit shorter, depending on how you approach this. So the requirement is going to be on the labs. And to specifically point at the types of things that you're mentioning, I appreciate the labs a lot, because the people who are working there are technical people, because they need to be technical. So you need to understand things of like, what are different processor architectures, and this processor is not the same as that one, and it does actually matter, like things that happen on code level. But they're lacking specific knowledge related to things that are important in this context, and I don't blame them, right? Things like knowing what is, let's say, a buffer overflow is something that is not understood by most, if not by any people who are working for the validation labs. And I don't blame them, because actually most universities are not teaching this. Are teaching general programming, but like you have to be really lucky and be in an exceptional place where people are not just saying like sometimes your code crashes, but actually how do you exploit a buffer overflow? What are the risks of doing this? How badly can a buffer overflow be? That's something that's typically not taught. And I would say that's something you actually see more broadly in the computer security community. like when I was at RSA last year, at the speakers lounge, right? So like not the general attendees, but the speakers. I figured out as I was saying what my talk was about, that actually most people are unaware of what buffer overflows are. Because most people are actually not actually programming, or if they are not aware of how to what details are about vulnerability research, or how to move further with types of bugs that you find. So then you were saying like, well, I want to come in and I want to say I have a proof in lean. I'd be surprised if people are familiar with proof assistance. That's one of the reasons to actually have this workshop, and to put people together and to discuss approaches. I do want to give you some positive feedback here as well. So when I spoke to the OpenSSL team last year, the team is quite new actually. Like many people have only joined in the last 1 or 2 years, are very, very recent to OpenSSL. And the type of technical knowledge of the new people who came in is extremely high. And they were having discussions with me about formal methods actually. So like I was surprised to hear this. That is, I think, also the right level to do these types of approaches, because, well, you'd like the people who are developing the code to make the formal checks of properties to be parts of the code development process, and not some separate afterthought that the lab does. And then also try to move whatever proofs you have along with the specification, that both get updated at the same time. But yeah, it's a whole community and like a lot of different moving parts, people that need to be brought together. And actually the challenge here is not so much improving OpenSSL, but it's actually a lot of the things that are currently passing the program are of very low quality. So how do you increase the bar for all the implementations, and then the most widely used ones will easily get through, but some of the worst ones will not, to have an even more secure implementation that has been very widely tested, might not have the same amount of impact. But then we need to see how to move the field and how to change the current standard practices. And that's going to involve bringing people together and discussing what is possible. I'm optimistic about this, and I hear that increasingly people are saying not, hey, can you do verification for me? But people are asking, can you help me? I'm doing the verification. So apparently there's a shift, according to some people that I've spoken to, in terms of understanding for the developers of cryptographic implementations. I hope that was a polite way to say the labs don't know lean, right?
Yeah.
And I didn't either until a year ago or so. I've done quite some lean and cock recently, but like I wasn't familiar with proof assistance before that.
Okay. Well, thank you, Nicky.
Thank you, James.
Let's give a round again.
Yeah.
Yeah. We can chat a little bit.
Yeah,
more.
sure. Yeah.